Hey, psst, come here for a sec. Take a look at this. What do you see? Well, if you said anything other than a better version of Microsoft Word, you are just about dead wrong. Most modern text editors are slow, buggy, and they downright slog to use. Is there really a need for 10,000 different features, linters, and copilots when I can just blow it out of the water with an alternative that's blazingly fast, compact, and much more stylish? I may have embellished some, or most, of that, just the tiniest bit, but there really is a text editor embedded into that GIF. Look, it says hello. Wanna know how I did it? First, let's talk about GIFs. Sure, you probably know what they are, I hope. But what about what's inside them? And don't get smart with me and say frames. By definition and observation, a GIF is a sequence of blocks where each block has a 1-byte introducer that tells you what follows. This is important because there are, surprisingly, quite a few types of blocks you'll find inside a GIF. First off, the introductory section, which starts with some headers, which identify the file as GIF. They are followed by the logical screen descriptor, which contains stuff like width, height, flags, background color index, and pixel aspect ratio, and then optionally a global color table, which defines the palette shared by all frames. And on the other end, there is the trailer, which marks the end of the file. But in between these two,
it's free real estate.
Sure, there is the obvious image descriptors which, as the name suggests, mark each individual frame in the GIF, which is what pretty much any program looks at when parsing or displaying a GIF, and coincidentally is what most people think a GIF exclusively contains. But here's where most people are wrong. There's also these weirdly underused data spaces called extension blocks. They come in 4 varieties. First, you have the graphic control extension, with which you specify transparency settings and control animations. Then you have the comment extension, which basically allows free text comments, but parsers may treat it as displayable text, so careful. Then you have the plain text extension if you want simple text overlays, and finally the application extension, which I guess they had no other idea how to name, so they went with an arbitrary one, cause it's just an identifier and then unlimited subblocks of custom binary payload. And what's wild is that the only really known public use of this is a Netscape 2.0. Yes, that Netscape extension used to loop an animated GIF file. In fact, this one is so obscure that most GIF parsers are unaware or simply ignore it, making it pretty much perfectly hidden. And I think you already guessed which part I'm going to sink my fangs into and make my own personal text editing playground. Now, before I dive headfirst into the how part, let's take one more detour in the what section. Text editors, to not even be more sluggish than they already are, internally all use opcodes to optimize the amount of data needed to update the contents of the edited file. This way we can have real-time online collaboration on documents, are able to undo or redo actions, and not have our computers freeze when editing a 400-page Steve Rogers and Bucky Barnes fanfic. Opcodes, short for operation codes, are compact instructions that describe what change happened, not the entire new file. Think of them as the diffs or edits you can replay to reconstruct every version of your document. Many editors keep an undo-redo stack as a list of opcodes, with each opcode being described as of a type, like insert, delete, set, with corresponding arguments like position, text payload, or length. For example, an insertion operation would look something like this, which translates to at position X add these bytes or characters. On the other hand, a deletion operation could look like this, which means remove n characters starting at X. In the case of a GIF, using opcodes to reconstruct the history of changes inside the text editor allows the block size to stay as compact as possible, while also making encoding and decoding really fast. Now, onto the writing code part of things. To make sure I didn't hallucinate all this information I just finished regurgitating to you, I started this project by making a script to inject some opcodes into a GIF and making sure they are actually properly stored there. Aside from some curating input, file management, and a couple more lines for the part where I handcraft an opcodes payload, the method which generates the application extension block is this compact 10-liner-ish. First off, the header, which is defined as follows. First, you have the value hex21, which identifies any extension block. Then, the extension label value. Each of those 4 I mentioned has one. In this case, hex FF. And finally, the block size, which is always hex 0b, meaning 11 bytes. The block size is also the reason why the identifier, which is arbitrary but I chose to be GIF edit 0, needs to be padded to reach that 11-byte length. After that, the payload is split as 255-byte data blocks, each preceded by a single length byte as per the format specs. At the end, a null terminator is added to mark the end of the extension block. With this, I can take whatever random GIF I come across and transform it into the perfect vessel for a hidden text editor. However, on the other side of the fence, things are a bit more complicated. So let's first walk through how a user should experience this, and in turn, how this program should handle it. First off, we take whichever GIF we fancy and load it in. Off the bat, we gotta parse it and decide if the GIF needs to be formatted, as with that script I talked about, or if there is already an application extension present with an optional list of opcodes. The first option is easy, just call the same method as before, then initialize all the other variables with their default values. The second, however, means that there may be opcodes already present, which need to be decoded from the payload, then loaded into the program. Now at this stage, the user can start using the text editor by inserting text, deleting characters, or moving the cursor. Each of these actions needs to be registered in memory as a stack, so that undoing and redoing actions is equal to pushing and popping the topmost element. When saving the GIF, it means taking all the new actions performed by the user from memory, encoding them into a new payload alongside the original ones, and then replacing the app block containing this new data. Right, let's zoom in a bit now. For loading the GIF, before taking the decision, first we gotta parse the buffer. We start by checking the first 6 bytes, as that's the header block size in every GIF. Then we skip the logical screen descriptor and optional global color table, if present. If you're curious, this check is done by verifying if the 7th bit is set in the logical screen descriptor, which, if true, means that the next 3 times 2 to the power of n plus 1 bytes in the stream are taken, where n is the size of the global color table. Afterwards, the bulk of the GIF file starts, where you find any and or all the extension blocks I've been talking so much about. So, from top to bottom, it's like this. If you come across a hex 3b, that's the trailer, which means end of file. If you come across a hex 2c, that's the label for an upcoming image descriptor. I'm not going to go too much into detail for this one, but here's a quick overview of the specs. And finally, if you come across a hex 21, that's the extension descriptor. Here we have 2 types of extensions. The application extension, which is identified by hex FF, and that you parse by applying that knowledge from creating the app block, and the others, which you can easily skip because the block size is constant across all of these different sections. Now, after it's parsed, we either use the build app block method to inject the new application extension block into the GIF buffer and set the opcode stack as empty, or we move on to decoding the payload to extract each stored opcode. And because you can't have one without the other, I'll go through the encoding and decoding at the same time. To each operation, I assigned an identifier, which is the first one written and read when dealing with any payload. Then, depending on the identifier, the upcoming data is handled differently. For insertion, because the inserted text length is not fixed, I first insert the length of the encoded string and then push the string into the buffer. For deletion and moving the cursor, I simply set the numbers of characters deleted or the new index. I opted to use 2 bytes for all the numbers to have more freedom with the operation, but this is kinda pushing it. You generally want to keep your ops as small as possible, and for stuff like insertion to further split into chunks if the size is too large. With these 2 methods, the opcodes can now be loaded into memory or saved to a file, while allowing anyone to interact with the editor using a much cleaner interface. This way I can use the editor like a normal human and… wait, what's this? Oh, thank you for reminding me, Mr. GIF Text Editor, that you can in fact like and subscribe if you're enjoying the video. Finally, saving the updated GIF file with the new text editor states added is done by first replacing the old app extension block, then calling the download action on the buffer reference. Replacing the app block is just going through the motions. Find the existing one, create a new one containing the updated opcodes list, and injecting this new data into place of the old one by accounting for the start and end of the old section. And well, this marks the end of the journey for this project. Of course, it's a pretty rudimentary implementation. More opcodes can be added to make the experience more fluid for the user. Just make sure you don't end up like all the existing editors where there are too many features that are just there for the sake of being there. For example, a periodic checkpoint opcode can be added to keep replay time reasonable, instead of loading and working with the entire editing history every time. Oh, and if you want to go even deeper, you can create a new application extension block for each historical editing segment, like per session, and apply the same mechanism to that as you do with the opcodes history.